Yes, madam, but screen is not visible.
Sir, can you hear me now?
Your voice is okay, madam. Screen is not visible.
That is automatically logging out, sir. That is a problem with Zoom.
Okay,
I
okay.
think the host disabled attendee screen sharing. So
yes, ma'am. I am making as a host. Now you can, ma'am.
So I cannot write on my board. I wanted to show you something, but it's not happening. No issues. Okay. So anyway, it is clear, right? The orthogonal frequency division multiplexing. Why we are going for from single carrier to the multi-carrier communication. As I said in my previous class, because using a single carrier, I could able to transmit some signals, even if you increase.
Madam, hello, madam.
Ma'am, your screen is not visible, ma'am.
Oh, my screen is not visible because I shared the screen, my desktop. Now it is visible.
Yes, ma'am.
Okay.
Is it visible? It is visible, ma'am.
Okay. So it is the OFDM actually, it is like your normal modulation technique, maybe AM, FM, TM, BPSK. These are all single carrier modulation techniques, right? So here the incoming data stream is modulated over a single carrier. But as I said earlier, when we want to improve the data rate, so we have to send your signals at a faster rate. When you are sending the signals at a faster, lower sampling time, lower symbol time, maybe 1 nanosecond, 1 microsecond, then there is a lot of other pulses are also joining into the communication channel because of the multipath communication. There is always an intersymbol interference, a severe intersymbol interference. This is happening because of your nature of your channel. That is, it is coming under a frequency fluctuated channel. Okay, so to avoid that one, we want to communicate in a normal communication. We want to do it in a normal flat fading channel. So what is the flat fading channel? The flat fading channel is irrespective of all the frequencies, whatever you are sending, it gives the same uniform distributed signal across your channels. So that means your channel is flat during your entire band of operation. But whereas when you are covering to the high frequency bands, the channel is not flat. It becomes frequency selective channel. So this frequency selective channel, I cannot go with your frequency selective channels because it is creating a lot of interference. So to avoid this one, still we want to go with a narrow band, but the same bands, maybe the multiple times, or I am having a huge bandwidth. So this huge bandwidth is divided into smaller bands. In each band, I will parallelly send my information. That's what I am interested in. Okay. So that comes under OFDM, orthogonal frequency division multiplexing. So this is actually a multi-carrier modulation technique. So this employs some carriers, allocated bandwidth, and convey the source to the destination using many of the formats of BPSK, QPSK, or QAM. So this orthogonal frequency division multiplexing is a special case of multi-carrier modulation scheme. So in which high data rate stream is actually split into small data rates, and it is OFDM is actually to avoid this frequency selective fading, it is taking flat fading communication, right? So this WFDM is actually having a problem by converting the entire frequency selective fading channel into a small flat fading channel. We know what is a wireless communication. We'll receive the signals through multipath communications. And I am giving an equation to my multipath communication as each path is coming through a different amplitude and different delays. So alpha i's and tau m's are delays and amplitudes of my multipath communication. So this multipath communication actually will distort the waveform of a given signal. So if you look at the diagram of a frequency selective fading, because of this large delay spread present in my channel, I am receiving different gains from through multipath communication. One is at 2 seconds, two is at 2.5 seconds, another one is at 3 seconds. So this is my different gains. When you add up all these things, there may be a possibility of destruction or obstruction, like destruction in the sense the whole signal is summed up and coming to a zero value, or it maybe gets amplified. Okay. So these problems, then how to tackle all these problems in frequency selective fading channels? We use the orthogonal frequency division multiplexing, OFDM. So this is actually taking different carriers of F1, F2, F3, F4, and the peak of the each signal actually coincides with the trough of the other signals. Okay. So generally we know what is orthogonal frequency division multiplexing. If you have two waveforms, suppose S1 of t and S2 of t, and if you multiply this S1 of t and S2 of t, integrate over that period of time, then those signals are giving me the output as 0. That is orthogonality. And we know what is orthonormal. Orthonormal in the sense unit energy. Suppose each signal is having a unit energy signal and it is normalized, we'll get the orthonormal basis functions. So then you may ask some questions regarding what is the difference between earlier, because we have used a frequency division multiplexing. Through this frequency division multiplexing, we used to accommodate many number of users into the communication channel. See, this is same as OFDM is same as your frequency division multiplexing, or it is something else. Okay. So I would say that it is something different from the previously used frequency division multiplexing because there is a large saving of bandwidth. So if you use, can you hear me, sir?
Yes, ma'am.
So if you use frequency division multiplexing, I have to use guard band between the channels. But whereas in OFDM, orthogonal frequency division multiplexing, we don't use guard band. We just place the carriers orthogonal to one another. So because of that, we are saving a large bandwidth in my spectrum. So when there is a large saving in the bandwidth of my spectrum, I can accommodate, even I can send more number of data at a faster parallel transform. So this design, how do you design this OFDM transmitter? So generally what we do, we take the bits, and while designing the OFDM transmitter, we need to consider how many number of subcarriers to transmit the given data signal. Okay. Suppose I want to transmit in my QAM format or my QPSK format. So QPSK format, in the sense it takes 2 bits at a time. Okay. I use maybe 10 number of carriers. So these 10 number of carriers, each carrier takes 2 bits because it is a QAM, it is a QPSK format. So 10 into 2, that means 20 bits. I have to wait till 20 bits of time. And these 20 bits are mapped according to my constellation diagram. Then they'll send across my all the subcarriers. So I will show you the diagram, how we are transmitted using orthogonal frequency division multiplexing. Okay, so this OFDM signal, just I'm quickly going through the slides because we need to complete the other modulation schemes as well. And also one student, one faculty asked for OTFS. I'll give you a brief introduction to the OTFS. So just finally I'm going through my block diagram. So we take the data stream and we'll wait according to your modulation scheme. we will wait. How many carriers you want to use? I want to use some k number of carriers. Okay, I have a huge bandwidth. I divided by that bandwidth by some k users. So I divide the bandwidth for k number of users, k number of data streams. So my data, my signal, that is the carriers are f0, f1, f of n minus 1, like that they are going on, f of k n minus 1. And I take the data. We'll wait till serial to parallel conversion, because my QPSK format or a QAM format. So if I'm in this example, suppose I'm taking 4 carriers and my constellation diagram, what I am using is QPSK. So in the QPSK, each carrier can take 2 bits at a time. Okay. So 4 into 2, 8. So till I arrive, till the transmitter is giving 8 bits, I'll wait at this point, serial to parallel point. Then these 8 bits are given to each of the path of S0, S1 and S of n minus 1. They are mapped. According to that, they are mapped. And suppose QPSK, the first data stream D0 equal to 0, 0. Then it is mapped to A plus J beta. Then D1, suppose it is 1, 0. Then it is mapped to minus A plus J beta. So like that, that amplitude is multiplied with sine 2 pi f naught of t. Then we summed up all the values, we'll transmit the signal over the air. This is general principle everyone knows, okay? So this is how suppose if I am doing a BPSK modulation scheme, my data is coming in at different intervals of time, T0, T1, T2, T3, and I'll wait serial to parallel converter, because I'm using D1, D2, D3, 4 carriers. So onto these 4 carriers, I'll port my data symbols. I'll port my data symbols using a BPSK stream. And these are all multiplied with sign carriers. So different sign carriers. And we sum up all the values we send across my OFDM modulator. And next instant of time, some other signals are coming. The 4 signals are coming, and we'll multiply those 4 signals with different carriers. We'll sum up all the values we send over the OFDM transmitter. Okay. If it is a QPSK, then I take 2 different intervals of time. Those data streams are combined as a symbol. Then the symbol is multiplied with my sign, and accordingly they are multiplied with different timing intervals. So then they will be modulated onto my OFDM carrier. So this OFDM carrier, actually we can represent this OFDM signal as your data stream multiplied by a carrier, sine 2 pi fn of t, right? So this can be easily represented using your known principles of your Fourier transforms. So actually we know very well that Fourier transforms break a signal into different frequency bins by multiplying the signal with a series of sinusoids. That is, if I have a writing pad, I would have explained you in a nice way, in a better way, because it's not allowing me to use my iPad. Okay, no problem. We have to adjust with this one. So this actually essentially translates the signal from time domain to frequency domain, or else I'll try to see with this notepad. Okay, but it takes time to draw the diagram. Okay, so we use IFFT and FFT as instead of generating independent carriers in the transmitter and the receiver, directly we can use the principle of IFFT block and FFT block at the receiver and the transmitter. So how it looks at the receiver and the transmitter. So if you use an FFT in frequency domain, my signals multiplied by sine and cos, right? So this is the representation followed by following the FFT equation. Similarly, IFFT equation, I'm using a frequency domain signal and they are multiplied by sine and cos. This resultant will give you a time domain signal. So in my transmitter and receiver, I can use these principles. There is a difference in the second equation. Actually, it is k equal to 0 to n minus 1, the IFFT equation, not the n. There is a printing mistake. The first equation is n equal to 0 to n minus 1. So I can use these orthonormal basis functions as your modulators. That is, we can replace the modulator using your IFFT and FFT block, right? So this IFFT, FFT actually they behave in a dual way. So these are all, these blocks are also we can interchange. And if you look at the answer is, these IFFT and FFT equations also, they come in handy in implementing and also in the conversion process. We can eliminate the individual sinusoidal multipliers required for the transmitter and receiver side. So the same constellation diagram, what we have seen earlier, a block which eliminates your generation of multiple carriers, that is sine of f naught, f1 and f of n minus 1 and so on and so forth, can be simply replaced with an IFFT block at the transmitting end. Okay. Similarly, at the receiving end, I can use an FFT block. It is an inverse operation. So I use the FFT block to remove, to translate your data stream into your normal BPSK PAM or PAM or BPSK format. We'll pass it through a parallel to serial converter. Finally, we can estimate what we have transmitted, that is D0, D1 and D of n minus 1. So these are all principles as of now, what I am saying. Everyone knows what is a OFDM. Okay. So, and also there is a role of cyclic prefix. Yesterday I talked about the cyclic prefix. So this is actually because of the non-ideal channel. There is some delay dispersion will happen in your communication channel. Because of this, there is a chance of intersymbol interference. And also on each subcarrier channel, due to this pulse overlapping, suppose there is a pulse overlapping because of this non-dispersive channel, there is always a chance of intersymbol interference and intercarrier interference due to the non-orthogonality. So, for example, if you generate sine 2 pi f naught of t, then sine 2 pi f naught of t plus some delta t. So, if these two multiplications, if they are not becoming zero, that means they are not orthogonal. So when they are not orthogonal, there is always chance of intercarrier interference. So this also happens in OFDM. So to avoid this intercarrier, to avoid this intersymbol interference, not the intercarrier interference, to avoid the intersymbol interference, we use a cyclic prefix. So we use some amount of cyclic prefix, that is what we are transmitting exactly at the beginning of your frame. Also, we'll add some content at end of the frame. Okay. So that is the way when you are decoding your signals, I can show you the diagram. So if you look at this one frame of data, that is a symbol energy spread across, actually we are transmitting n data streams, but we are also adding NC chip bits extra. So these NC chips are nothing but the last values of your data stream are added at the beginning of your cyclic prefix. So this is an additional redundancy we are keeping at the front of your frame. So then what is the advantage if you add this redundancy at the front of your frame? So when I am receiving, if there is an intersymbol interference, because I know very well that the last part is joining with the first part. Okay. So what I do, my idea is I don't decode this last part, or I don't decode the first part of my frame. I start my decoding only after the cyclic prefix. So that's where I can avoid the intersymbol interference in OFDM. And if you look at the total block diagram of the OFDM, that is the constellation diagram. From the block diagram of OFDM, after addition of the cyclic prefix, we can see that only the extra addition to this one is we have added a cyclic prefix at the end of the frame. Okay, so we have added a cyclic prefix at the end of the frame. So suppose if you are sending x0 to x of n minus 1, we'll add an additional numbers, that is x of n minus 1 to x of n minus ncp data bits additionally at the cyclic prefix. And we remove the same cyclic prefix After that, we'll send those signals to the FFT block, and we do the frequency equalization, we do the constellation demapping, and we go to the parallel to serial to parallel decoding scheme. Okay, so the key ideas behind adding the cyclic prefix is, actually we are converting a linear convolution into a cyclic convolution. We know what is linear convolution and what is cyclic convolution. So linear convolution in the sense, when you convolve two signals, suppose two rectangular signals, the convolution between these them will result into a triangular waveform. Okay. Similarly, if you are convolving a long signal with a short signal, then generally the time duration of your convolution will be the two signals sum plus some extra bit, that is 1. Suppose x and y, okay, m and n, then m plus n plus 1 data bits will be seen at the output of the convolution. But whereas in circular convolution, we are moving in a modular form, so we come back to the original shape. That is what the circular convolution we do in OFDM. So this helps in combating ISI and ICC. Okay. So what are the other advantages of OFDM? So this permits, actually we can send densely packed and overlapping subcarriers. And also it's spectrally efficient transmission scheme. Why it is spectrally efficient? Because we are saving some bandwidth, right? Because if you use the frequency division multiplexing, we have to always leave some parts of the guard band, whereas in OFDM, we are not leaving any guard band interval between the carriers. We are using orthonormal subcarriers, so spectrally it is more efficient. And also, the another most important advantage is the digitally it can be implemented. That means it is fast and efficient signal processing scheme. And also it supports different modulation schemes based on the channel conditions. We can avoid any equalizers as well in this communication. So currently we are using this OFDM in LTE, LTE advanced, DVB, T/2 terrestrial telecommunication, as well as 802.11a and 802.11g, 11n, 11ac, 11ad. In all these wireless standards, currently we are using OFDM. And also in WiMAX, that is worldwide interoperability for microwave access. LTE advanced and 4G mobile phone standards also. Currently we are using OFDM transmission scheme. And also as per the present scenario, the standards given by IMTT 2020, they're also given a green signal to use the OFDM even into the 5G communication. Okay. So with this, just I have given a brief introduction to the OFDM because I am quickly rushing through the slides. Then if you want to ask me some questions in OFDM, you can stop me in between. If you have no questions, then I'll go to the next presentation.
Good afternoon, ma'am.
Yeah.
Ma'am, is the size of IF50 and subcarriers, number of subcarriers selection need to be same, ma'am?
Yes, need to be same because you are using endpoint FFT, right? So in
Yes,
the endpoint FFT, suppose if you take an FFT signal n equal to 0 to n minus 1, you'll use your x of n, that is your data symbols, right? And e power j 2 pi fct, that is your
yes.
FFT equation. FCT in the sense you have to translate into a digital domain. So it is actually e power j 2 pi some k by n and small n.
Yes.
Okay. So then how many number of subcarriers you are using and what is your data strength? That must be matching. Otherwise, I cannot accommodate all my symbols into my FFT block. So that is always necessary.
Okay. Okay.
So any other doubts?
Yes, madam. In chat box, one participant raised one doubt.
Okay.
Sir, Hanumantarao sir, are you there? Okay. Which constellation mapping is better, QPSK or QAM? Why?
QPSK, QM. So the basic modulation schemes. If you have studied about the different modulation techniques available in our communication, digital communication. So as I said, if you go for a BPSK, from BPSK, if you go to the QPSK, from QPSK, if you go to the QAM, what is the advantage we are gaining from one modulation to the other modulation? So BPSK, the distance wise, they are separated, right? One is on the right side, another one is on the right left hand side. And also we have derived the probability of error equations. Like I can show my one of my note. In this pad, I could not open. Okay, advanced digital communication. ADC lecture notes. Okay, right. I'm just giving quickly reviewing what is the probability of error derived for BPSK case. So if you see that the probability of error of a BPSK case is Q of mod of S by 2 sigma. S means your transmitted signal distance. Okay. This is the probability of error for BPSK. Similarly, if you go for QPSK scheme, I can show you how we have derived for the QPSK scheme. Finally, we have derived for QPSK is my detection scheme. So it's a very lengthy process, right? So for channel 1 and channel 2, finally we have derived the QPSK bit error rate is 2 times EB by N naught, root 2 times EB by N naught. Okay, and for BPSK also we have I said it is mod of S by sigma. Mod of S by sigma means energy of your pulse. So that is EB by N naught. EB by N naught. So what we are understanding that the probability of error is an argument of your Q function. And when the argument is increasing, the probability of error, because it is inversely proportional. The Q function is a waterfalling nature. So when Q of something X, Q of X, if X is more, the probability of error is less. If X is less, the probability of error is more. So in that case, here for QPSK, I am getting 2 times. Whereas for BPSK, I am getting only single time. That is root EB by N naught. So which probability error is more? The first one or the second one? Sorry, QPSK, I am getting EB by N naught. So final, I can show you the final probability of error. This is my probability of error of my QPSK. Because one channel only I showed. So for QPSK, I am getting 2 times Q of something, whereas BPSK, I get only Q of the internal part of 2 times 2 of EB by N naught. So naturally, when you are keeping more number of points in the constellation diagram, the probability of error is also going to increase. So if you ask from BPSK to QPSK to QAM, naturally the distance between the points is very less. So your detection area is also going to reduced. So because of that, we are getting a huge amount of probability of error. So that depends. If you use QAM, if you use QPSK, if you use BPSK, the modulation schemes remain same. The probability of error remains same. The transmission technology we have changed. Earlier we have transported through a single carrier. Now we are transporting through a multi-carrier communication. Okay, so I think I have answered your question.
Yes, madam. exactly.
Okay, okay.
Madam,
Uh,
at the same time, madam, one more participant requested to us,
mm,
madam, could you please suggest any standard textbook for
mhm.
understanding of the OFDM?
Understanding of the OFDM. Standard
Yes.
textbook. Uh, so there are many textbooks on OFDM. MIMO OFDM wireless communication by Cho. I think the Cho is the best book. He explains very neatly each point, and also he starts from the basic digital communication modulation schemes. Okay,
Yes, madam. I
there are
hope
many
Sudhir
books.
Kumar. Yes, madam. Thank you.
Okay, if there are
Then
no
it's our.
doubts,
Yes, madam. No doubts.
okay, then I'll quickly move to the next session.
Yes,
Okay, just I think yes. So this is the visualization from one of the paper. You can see that how the OFDM works. If you are sending your signals through a single tap, I'm getting through a single carrier communication, I'm getting some information. But the same signal, if we are sending through a shower, right? This is a shower. So from the shower, each drop is coming out. So this each drop carries following a flat fading channel. But if you are continuously sending through a tap, it follows under frequency selective channels. So because of that, the probability of error is also going to increase. Your OFDM is nothing but a truck company which takes all their consignment into one single lorry. But when it is come to the OFDM, that is a single carrier. When it is come to the OFDM, it loads sub-components of your truck into different trucks and it transports the system very smooth way at same instant of time. This is the difference between OFDM to the frequency division multiplexing. And also what is orthogonality I said earlier, right? So you can refer this paper and you can understand very well how the OFDM works. I'm sharing this paper. So this paper is orthogonal frequency division multiplexing tutorial. So intuitive guide to principles of communication. You can go through these modulation schemes. So there are different modulation schemes. Everything is clearly explained and is also easy to understand. And also mathematical notations are given, very fancy notations are given. They are all very easy to understand if you want to work on your orthogonal frequency division multiplexing. Okay. And Kiran Mai, how much time I have still?
ma'am. For the first session, 1.5 hours, ma'am.
One and
So
a half.
we are
Okay.
1.5 hours, ma'am.
Mm,
So we have started at 2:15, no, ma'am.
mm.
So 3:45 time is there for the first session, ma'am.
Okay. I have
Second
one
session
session.
we started, ma'am.
I have one session or two sessions today.
2 sessions, ma'am. 2 sessions
Okay,
today.
okay. I'm thinking that I'm only having one session, so I'm rushing
No, ma'am.
through each slide.
No, no, no. 2 sessions.
Okay, okay. It's very nice.
Okay.
Right. So shall I go deep into the OFDM or can I go to the next scheme?
Yes, madam.
So I can go to the next session, right?
Yes, ma'am.
Okay. So the next modulation scheme is actually, I can show you a filter bank, or before I complete generalized frequency division multiplexing, I'll come back to filter bank. Okay, that will be nice. Right, okay. Just a minute. This is not my presentation. Okay, just start with some introduction because it takes some time to locate my PPTs. Mm. So why we are moving from 4G to 5G, right? So from OFDM and GFDM and other systems. Actually, my PPT is located somewhere, but I have taken some other PPT, no issue. So this OFDM and GFDM and what we have done in our laboratory also I can show you. We built a test bed for GFDM and we could able to publish some papers, a good number of papers on GFDM system. So just now we have seen the OFDM, orthogonal frequency division multiplexing. It is actually a kind of a multi-carrier system with the orthogonality between the subcarriers. Okay. So we have seen that actually these orthogonality between the subcarriers and also avoids intersymbol interference, and also we can accommodate more number of subcarriers, so we can save the bandwidth, and also it is easier to equalization as well. These are all the advantages we have just now we have seen in your multi-carrier communication. So um, so what is the main disadvantage in YFDM? If I ask you a question on what are the main disadvantages in GFDM, is the orthogonal carriers, right? IFFT and FFT. So this IFFT block and FFT block we are designing over here. Suppose IFFT block is generated with different multi-carriers, that is with sine 2 pi f naught of t, fn of t, and f3 of t, and so on and so forth. And in case at the receiving end, the FFT block also should able to generate the same amount of multi-carrier frequency. So from the transmitting end to the receiving end, if there is some value of a delta variation from one point to the other point, naturally it leads to an intercarrier interference. Okay. So that means we need a strict orthogonality between the subcarriers. So no one will guarantee you that your system will give you a strict orthogonality. Even if you maintain your electronics is perfect, even after the ambient temperature also it is working in a quite natural way, even then there is always a problem of intersymbol interference and intercarrier interference, and also the main problem is strict orthogonality. Okay, so then if you need, suppose some deviation is there in the transmitting frequency to the receiving frequency, that sine of omega naught t plus delta of t. The delta of t is an additional phase. So this additional phase will lead to a problem of synchronization. Then is there any better method where we can go for, we can little bit leverage can be given for synchronization of your communication system, right? So that synchronization issue actually can be resolved using another new waveform. Just give me some time. I'm trying to join with my iPad one more time. So if I can check with sir, you have I join with meeting ID, right?
Yes, ma'am. User, ma'am.
Join with user, join with the personal link name, right?
Yes, yes, ma'am.
Okay. What is the personal link name you have given? Is this Dr. VV Mani or VV Mani?
User, ma'am. It is renamed as user again.
No, now I am trying to join through my iPad.
Okay,
So
ma'am.
already I joined through laptop.
Okay, that name is user.
No, iPad name is not user. That name is user. You have given
User.
access to the user.
User, yes, ma'am.
Okay, now I am joining through iPad.
Okay, ma'am. Okay.
So what shall I write here? Join with meeting ID or join with
Anything, madam, no issue. You can join with ID or also you can join with the link.
sir, can you repeat the ID one more time?
Sure, madam.
So because here I have some time, no, so I can explain in detail, but I don't know why it is not allowing me to do with my pad.
Madam, ID 870
870
4650
4650
3257.
3257. Okay,
Yes, madam.
I'm joining.
Passcode
1 minute,
12345.
1 minute, sir. 1 2 3 4 5. Yes. So can you see a new user joined here?
What's the name, madam, for new user?
New
If you
user.
please raise your hand from new user.
Sir, where can I see the tries hand?
In more, madam, there is. Madam, I think there is a Priscilla, Glory Priscilla. Who is that?
There are symbols are coming like join audio, start video, and share screen, participants, more. Yes. In the more. But before I click that more, it is asking to hear others, please join audio.
Yes, madam. You can join with audio.
Hmm. I could see the screen, what I am sharing in my other laptop.
Ma'am, we got it. I am giving a co-host, ma'am.
Hmm.
Dr. V.V. Mani,
But
NIT Warangal.
yes, yes.
Yes, ma'am.
So now I can share my screen, right?
Yes, madam.
From both the sessions, I can share my screen.
Okay.
Yes, no issue.
But here I should stop sharing my screen from the another. Okay, I'm sharing. Start share. This will stop others screen sharing. Do you want to continue us? Okay. Okay, right.
It's visible, madam.
Yes, sir. Yes, sir. Yes, sir. Okay. Here, what I want to tell you is orthogonal frequency division multiplexing, right? OFDM. So as I said earlier, in my we have X case. We have X case, or this is my digital domain. This is my frequency domain, and X small x of n is time domain signal. Okay. So if x of n is given to your frequency band, that is your OFDM block, we know very well that is e power j 2 pi minus 2 pi k small n by capital N. This is the equation to compute your frequency domain equations. So here I can even open this one as cos 2 pi k small n by capital N with a minus sign. So it is sine 2 pi k n by capital N. And the summation of n equal to 0 to n minus 1 x of n. Okay. So these are the equations I am using. So when I am using these kind of equations, what I would like to say in OFDM, the major drawback in OFDM is, so I have to, for IFFT, this is at maybe if it is plus, so if I use plus, I said I would use K and the small x of n. This is my transmitting side. So this is my transmitting side. My transmitter, TX. Okay. So what about the receiver? In the receiver, so in the TX, I use IFFT block. I use IFFT block. In the this is at this is at transmitter. I use IFFT block. At the receiver, what I use So at the transmitting end, I am using cos 2 pi kn by capital N, right? These are my two carriers, orthogonal carriers, cos and sine orthogonal carriers. At the receiving end, I receive x of n. So I receive x of n. I implement my, sorry, I receive x of, what I receive? I give x of k. So I give x of k, so I receive x of n. This is my transmitter. So to these signals, I can compute the frequency domain. That is e power minus j 2 pi k n by capital N. This gives me back again x of k. That means the summation x of n and cos 2 pi k n by capital N minus sine 2 pi kn by capital N. This is my equation, right? So one is IFFT and another one is FFT. So this one is FFT. This one is my FFT block. So what I am saying, a strict synchronization is very much essential in communication. So strict synchronization in the sense, when I am transmitting my signal, I use cos. So 2 pi kn by n. When I receive my signal, I have to use the same cos. That is cos 2 pi kn by capital N. If you don't use the same cos and same sine, if there is a deviation from the cos and sine, instead of generating this cos, suppose my electronics is generated cos 2 pi k small n by capital N plus some 2 pi times maybe some n dash, because it is a phase, right? So I used a phase, 2 pi n dash phase, additional phase is generated. Then what will happen? So can you decode your signals? No, because always we do multiplication process, IFFT, FFT. I receive this kind of a signal. I'll multiply again with this kind of a signal. That means my original cos 2 pi k small n by capital N, this time is multiplied by cos 2 pi k small n by capital N plus some 2 pi into n dash, right? So if it is, if you don't have this 2 pi n dash, this simply can be written as cos square. That means 1 plus cos 4 pi k n by capital N, right? So this we can be removed using your matched filter. Only the constants will remain. From the constants, I can decode my data stream. But because of your 2 pi 2n, it is not exactly cos A and cos A again. It is cos A into cos A plus B. So there is some residual point is coming into your communication. So this residual point will create lot of disturbance in my communication channel. So this is the major drawback, major synchronization issue in OFDM. So to avoid this major synchronization issue in OFDM, we are proposing a new stream. So we are proposing a new stream, proposing a new scheme, that is, so can you see the?
Yes, ma'am. Yes, ma'am.
Can you see my new screen?
Yes, ma'am. Yes, ma'am.
Okay.
Proceed.
Yeah. So I am going to, that means you are controlling from your side, no? Karan Mai? Only one screen, only one person can present at a time, right?
Yes, madam. Only one person can present at one time.
One time. I cannot present from both the sessions. So this option is available in WebEx. Okay.
WebEx, yes,
I can present through multiple devices. Okay. So no issue. Right. So we need a strict synchronization. So we need a strict synchronization. So why? But even then, we adopt OFDM only in 4G. Why we adopted 4G? Because of the availability of your FFT and IFFT filter banks, right? So it takes time to turn on the cell phone. Like there are several disadvantages about OFDM. One is the sensitivity to frequency shift. The frequency shift just now explained, cos 2 pi and dash. So this sensitivity will leads to a wrong errors. That is, it leads to a lot of probability of error is going to increase. And the transmitter and receiver need very strict synchronization. So, and also it is very crucial thing in communication. Okay. Now, there are several disadvantages about OFDM as well. That is, there is a large out of band radiation. If you look at the large out of band radiation, the power leakage affects the user in the near band. So the inside band, OFDM with 200 subcarriers, if you plot that equation of the power spectral density, then at the above we have power spectral density, it starts from 0, and as the frequency is increasing, it is going to minus minimum of some 20 dBs, minus 20 dB on the other side. So there is a large amount of power is deviated into the next bands, the other bands. This is one of the disadvantages in OFDM. But we will overcome these disadvantages in generalized frequency division multiplexing system. Okay. So this that is 5G, but this slide is actually very old slide, because that time even even the standards have not come up, and the researchers have worked on generalized frequency division multiplexing, and they started doing publications in GFTM, and they thought GFTM would definitely come as one of the standard for 5G, but finally they'll end up with only OFDM because of some other disadvantages with GFTM. Even though it is spectrally efficient and we can save more bandwidth, but still, as I said earlier yesterday, we have to entirely shift your base stations to a new base station. It's not possible, right? The existing infrastructure, if you change a totally a new paradigm, then it takes a lot of money. A lot of economy has to be deployed onto the base stations. So it's not a feasible solution. So people thought, again, they come back to OFDM. But even then, we need to understand what is generalized frequency division multiplexing system. So this generalized frequency division multiplexing system is also a kind of a multi-carrier system with circular pulse shaping towards the data. Anyway, in OFDM also, I said, when you are using a linear convolution, your data stream is going to stretch to a long data stream. But if you use a cyclic prefix, the last part is converted back into the first part that comes under a circular convolution. So this is also a kind of follows a circular convolution. But here, what extra thing we are using for generalized frequency division multiplexing is we use some pulse shaping filters, a circularly pulse shaping filters towards your data. Okay, that means we are confining your band to your own band. We are not deviating from one band to the other band. Okay, so this confinement we are doing through some pulse shaping filters. Whereas in OFDM, as it is, we are transporting the data onto your multi-carriers. But here in GFDM, we pass the signal through a filter, that means a shaping filter, then we'll port that data onto your multi-carrier communication. That is the difference from a GFDM to a OFDM. In a pictorial graph, I can show you the difference from a GFDM to a OFDM. And also we use a matrix notation. So the complexity of the system is also more compared to OFDM, because in the OFDM, using FFT and IFFT, I can show my entire transmitter and receiver. Whereas in GFDM, I have to use certain mathematics to show what is my transmission, and what is my reception data stream constructed with the prototype filter. Okay, so there are some advantages. because it takes lower out of band radiation. And also strict synchronization is very much essential in OFDM. So it gives some relaxation, not totally relaxed, but some relaxation of the frequency synchronization is there. And so because this is again connected with applications, Internet of Things, machine to machine communication, and other applications are present. No? So we always say this is more advantageous than the other one. Okay. Now, just look at the equations what we are using. A normalized P point DFT. So a normalized P point DFT. So if you look at this equation, e power j 2 pi, earlier I wrote k into n by capital N, right? So instead of k, instead of n, here we used p. That's only the difference. So a normalized p point DFT matrix, if you take e power j 2 pi mn by p, normalized with the root value of p, and p belongs to a natural integer. Okay, and we use sync x, that is a periodic sync function. We use a sync x. We know that sync x is sin pi x by pi x. Okay. Also, I can use a different mathematics. So a transceiver block diagram, how it is generalized. Here I don't think I can explain without using my notepad. Okay, I'll try to explain it. So in the GFDM transmitter, we take the data stream and translate this data stream into a matrix A. I'll show you in other slides because it is given in other slides. What is the matrix A? And then we wait for parallel to serial conversion. We also add a cyclic prefix and pass it through the channel. This A is your modulator. So what is that modulator? Modulator is a GFDM modulator. Okay. The same scenarios, again, convert into parallel to serial, add cyclic prefix and pass it through the channel and receive through the channel. That means remove your cyclic prefix and serial to parallel conversion and use a demodulator. That is, the demodulator is functioning on B and estimate your data symbols. So A is a modulator and B is a demodulator. How it is different from OFDM, that is the concern for us, right? So here the subsymbols, what I am saying is total is equivalent to D. The D is K into M symbols. So your the data vector. So D means your data vector, this data vector. Okay, the small d, D of L. That means D cross 1 vector. This D of L is a D cross 1 vector. So this D of L of K plus MK, that is the mth symbol on the kth subcarrier. Because I said in your OFDM, to go back to the OFDM. Yeah, if you go back to the OFDM, here we use a mapper and a pilot insertion, guard insertion. After that, I use IFFT block, right? So this IFFT block is now taking in this format A. I take data symbols, D data symbols at a time. And this D involves what is the subsymbol notation? Mth subsymbol onto the kth subcarrier I am transmitting. Okay. So these D data symbols are actually, the total data symbols are actually K into M data symbols. K is my subcarrier index and M is my subsymbol index. I'll show you in another diagram how it is exactly looks. So if you look at the transmitter, we use some filters. So these are all the filter structures. There are M subsymbols here. So these M subsymbols are going through a transmitter matrix. So these transmitter matrix are going from 0. So first on first subcarrier, right? So mth symbol, right? So what is the difference from OFDM to GFDM is on K subcarriers and K subcarriers, we are sending the same data symbol 0, 0, 0. Again, next K subcarriers, I'm sending the first symbol repeatedly. And at the end, and an mth subcarrier, mth subsymbols, I'm sending on K subcarriers. I'll show you the exact diagram. So here, a prototype filter is used. That is G of G00. This is actually coming from a construction of your data stream A. So this prototype filter is actually a modular filter. Modular in the sense, suppose 4 into 2 equal to 8. So, but it leads to 10. Then the 2 coming back to 8, we will adjust into the 8 itself. Okay, that's why we come to the modulo operation. This is similar to your modulo operation. So this modular operation, G of n minus mk, this is a modulo operation. And your n is moving from 0 to d minus 1. So this is a frequency domain prototype filter is used. Then we'll arrange them in a matrix format, that is root d times w times wd into g. This gives the transmitted signal. Okay, maybe it's not clear in this mathematics, but I can explain you through other slides where you can easily understand through your diagrams, because a lot of mathematics involved in GFDM. So finally, a digital baseband filter, digital baseband signal looks like similar to IFFT here. Similar to IFFT, just scrolling down my cursor, e power j 2 pi k n by capital K. This is your IFFT block. Okay. So to this IFFT, what we have done earlier, just a data symbol is added. Now in this case, to this IFFT block, we are adding a data symbol convolved with your filter bank. This is the filter. G of M is the filter. So this G of M is actually a circularly pulse-shaped filter. Here you can see the modulo of G, n minus mk minus L over the D. Over the D, it comes back to the original value. So that is an additional precaution is taken onto your signal, such that the out of band radiations it eliminates, and also it restricts your signal into a strict synchronization. So synchronization is deployed, even they are non-orthogonal signals, but they are restricted in some nature of a filter. Okay, so now, so the GFDM works with the channel and the receiver. So we can estimate the signals using MMSC, MMSC and MSC, MSC and zero forcing receivers. So that depends. The OFDM is actually, my subsymbols are equivalent to 1. My K equal to D data symbols. But if it is GFDM, K into M is equivalent to D. So K into M is equivalent to D. Here we use a Dirichlet pulse, a root-raised cosine pulse, and maybe the spectrally efficient pulses, where gives the better out-of-band leakage to your GFDM systems. So are there any doubts in the GFDM? Because it's purely a mathematical equations I'm dealing with. So if there are no doubts, then I'll continue with the presentation.
No.
Okay, madam.
Because it is too mathematical in the nature. So, you know, I just skip all these mathematics. The performance, filter optimization and out of band, the filter with minimum the parameter settings. I just skip the power spectral density. So if you look at the power spectral density of a GFDM model using different filter banks, one is optimized filter, root-raised cosine filter, and Dirichlet filter, and your normal OFDM. So the normal OFDM is actually a blue color one. Okay, green color one. The normal OFDM is a green color one. But what we are trying to do in GFDM, by using different filter banks, filter shapes, we are trying to reduce the out of band radiations. That means the green color, we are trying to bring it down to the lower range. Green, we are trying to bring it down to the lower range. So that is happened through your RC, root cosine pulse in red, as well as a Dirichlet pulse in even yellow, right? And RC filter with alpha equal to 0.5 factor, it is in the red color. They are much better than your normal OFDM scheme, and even optimized filter is giving a best performance out of all the radiation patterns, because it is restricted to only a certain band, whereas the other schemes, RC Dirichlet and OFDM, they are leaking into the other bands. Okay, and the symbol error rate using the different schemes for the GFDM is also analyzed. From suppose in this case it is OFDM2 with some factors of this data scheme, how the and also one more thing you have to I forgot to mention here, because naturally the GFDM gives a better performance than OFDM gives a better performance than a GFDM. But what for we are going for GFDM? Because of this localization. That means it is non-orthogonal, but still we can make your signals to decode perfect in nature. That's the only advantage with the GFDM. So what I want to say is SCR performance, that is symbol error performance of GFDM and OFDM can be the same, but not exactly the same. Okay, this is what the observation of the researchers, the GFDM to OFDM. Okay. So this is the work done in my laboratory. So I can show you the test bed what we have developed for 5G communication in our wireless communication laboratory of NIT Warangal. You can see we have used transmitter and receiver using USRPs, the real-time communication. So, and we have built a GFDM modulator and a demodulator. And also we have measured the power spectral density of the transmitted signal as well as the received signal. The transmitted signal I and Q forms, the received signal I and Q forms, and their bit error rate is also evaluated. For pictures, to show the entire picture in one sector, we placed both the transmitter and receiver nearby. But frankly speaking, these transmitter and receiver kept it two different locations, and we have measured the distance. We have measured the communication link. So you can see the transmitter and transmitter I and Q transmitted data and their power spectral density, PSD. So this whole analysis, the baseband signals we have constructed in LabVIEW, and then it is ported onto the USRP. So from USRP, it goes to the channel, goes to the channel in air, goes to the air. So from the air, we start decoding the signals. So here, the exact timing is also important. So we have implemented new algorithms for timing synchronization as well as the carrier synchronization. So both the synchronization algorithms we have targeted, and also we could able to publish a good work based on this test bed. So this is my receiver. So we can see that the transmitter to the receiver, the transmission is started exactly at the 0th axis. But whereas the reception is started after certain time. But my decoding scheme, I don't know whether my decoding I have to start at 0 point or I have to start it at this point, because I don't know when my received signal is occurring to my receiver. So what exactly we have to do? We have to estimate this time. We have to estimate this null time. After estimating the null time, from that time onwards, we start decoding your signals. So this is what we have done in our communication laboratory. So my transmitted constellation diagram, my received constellation diagram, I forgot to mention that what SNR, it is this constellation diagram looks like. And is also the power is increased. So when the power is increased, the constellation is coming across the localized to their respective positions. Even if you further increase the power levels, it is the constellation diagram is isolated to their independent locations. So we could able to see the outputs at the receiver. Okay, this is what a simple example, but I'll take you through my other slides where exactly what we have done for your for my VLC communication, for my GFDM communication. Okay. So Kiranmai.
Yes, madam.
So shall I continue, or what's your opinion?
Ma'am, if you want to take break, ma'am, for 15 minutes,
Okay.
because
Okay.
you are continuously giving lecture. Na?
Yeah. So today morning I started at 11. That is my regular class hour. So 11
Yeah,
to
ma'am.
11 to 1. And
Okay.
again it went up to 1:30.
Yeah.
Some little lunch, and after that I came back to. But unfortunately, I could not use my pad. That's a bad thing. Otherwise, I can write something. I can show you the mathematics. What is hidden in my GFTM.
No problem, ma'am. No problem, ma'am. So
Okay.
take a 15 minutes break, ma'am. We will start
Okay.
after 15 minutes.
Okay. Okay. Thank you so much.
Okay. Thank you, ma'am. Thank you. Participants, please take 15 minutes break. Okay. Don't leave the meeting. After 15 minutes, the session will go on. Okay.
Sir, can I start my presentation?
Ma'am?
Yes, madam.
Yeah.
Okay. Go on, ma'am.
Yes. So it is allowing me to share for only certain time. Okay. So here I talk in deep about GFDM, what we have done at NIT Varangal. What is this physical layer waveform? Okay, and the transceiver model of a GFDM system. So this one is actually the generalized frequency division multiplexing, the GFDM model, and first work is with additive white Gaussian noise channel, and then we implemented with the relay fading channel, and different analysis is also carried out. Okay. So anyway, introduction part, the same notations, everything. I just go ahead quickly. And already I said the advantage from GFDM to YFDM because the out of band leakage is less in GFDM, and strict synchronization is not necessary for the GFDM systems. Okay. Then directly I am moving to some of the drawbacks. We have already discussed about these drawbacks. That is cyclic prefix is taking some amount of bandwidth. And this also, this actually we have introduced the cyclic compacting ISI results in spectral sensitive to carrier offset and higher cost of amplifiers. Okay. So these 5G scenarios in my yesterday's lecture, URL is URLL, that is ultra reliable low latency, and best experience when you are moving the aeroplane, when you move in the speed trains. So this is we should feel the best experience of your internet. That is a 5G motto, and everything is connected to the cloud. Okay, here. So to achieve all these requirements, as I said, massive MIMO, millimeter wave bands, and new physical layer waveforms. So MIMO is already is a known concept. So quickly I am going through some of the millimeter wave band. So because this millimeter wave communication is directly capacity of your channel is directly proportional to your bandwidth B. Okay. So because in millimeter wave the bandwidth is more, so naturally the capacity is more. But we need a line of sight link for wireless access networks. So and at 6 gigahertz standardization is done for WPAN and WLAN and block hole cellular networks. Here the main issue is in millimeter wave bands, the propagation is an issue. Why propagation is an issue? At higher frequencies, the wavelength is small, right? So that means the wave propagates in a smaller distance. So it cannot be propagated to a longer distance. That is the one important issue. And also there is a loss of more of wastage of power. And we need very high directive beams. Suppose we have a building in between the transmitter and the receiver. Then at the other end, I cannot receive anything because of the low directivity of your system. And also signal attenuation reduces interference, and very line of sight propagation is very much important in millimeter wave communications. So these millimeter wave communications, the practical issues, we have large bandwidth. So we thought we can increase the higher noise power, but we need a directive beams for concentrating the power. And also a small scale fading modeling, heavy shadowing modeling, and efficient hardware implementation, because in millimeter wave the bandwidth is more, so your sampling frequency is also much lower, right? So we need fast samplers. That's not possible in your devices. So we are moving to that is the one band where we use a communication. Anyway, I'll tell you that millimeter wave communication, how it is useful, and how we do the beamforming in a separate slides. Now come back to the GFTM. I explained in a physical layer thing, the new waveform is GFTM. So this GFTM is already, I said, it's a non-orthogonal block-based multi-carrier technique. And actually it is covering OFDM and single carrier frequency division equalization as a special case. Okay. So how my GFTM is different from OFDM? That's my understanding. So here the difference is the data source is same. Any mapper, maybe QAM, PAM or BPSK, QPSK, any mapper we use, that is also same. Instead of OFDM modulator, it is replaced with a GFDM. Here in the case, we also add cyclic prefix for the OFDM. In GFDM also we add some cyclic prefix, right? Then it goes through the wireless channel. We remove the cyclic prefix, we do some equalization, and channel estimation and synchronization are the most important issues in GFDM. And we go through the GFDM demodulator, then we use a detector, either matched filter, zero forcing, or MMSC filter, and we do the demapping and we take data estimation. Okay, a typical block diagram of a GFDM modulator looks in this fashion. So what is new to us? The new is only a GFDM modulator. Okay, this new thing is GFDM modulator. So we try to understand how the GFDM modulator is constructed. So this GFDM modulator, so this GFDM modulator, if you look at the GFDM modulator, you can see that we can easily identify the difference from GFDM to OFDM. Okay, so what is the difference from GFDM to OFDM? Here in OFDM, we have blue color is a cyclic prefix, then followed by time samples. On each subcarrier, we are sending a cyclic prefix and data symbols. Okay, n time samples we are sending, n time samples and a cyclic prefix. Like that, on all the subcarriers, we are sending time samples and cyclic prefix. Okay, that we understood very well. Then coming to the frequency division multiplexing. So what is frequency division multiplexing? On each frequency, we send a different data, right? So along the vertical axis, if you look at along the vertical axis, we have a cyclic prefix in the blue color, and light blue, there is subcarriers. So in all these subcarriers, I am sending n symbols. So try to see this one. We are sending n symbols. Okay. So these n symbols are onto each subcarrier. And n frequency samples. Now, how these two are merged together to go to GFDM, frequency division multiplexing, generalized frequency division multiplexing. If you look at this scenario, my n is actually k into m. So I'm using n time samples, right? Across all the n subcarriers, I'm using n time samples. That means on each subcarrier, I'm using capital N number of subcarriers, capital N number of time samples. So in GFDM, what we are doing, there are k number of subcarriers. If you look at the GFDM, k number of subcarriers along the vertical axis. Okay, the green color. The green is n is equal to your time samples. So these time samples are divided into k and capital M. That means k number of subcarriers, m number of subsymbols. Okay. So I take k time samples, not n time samples. I take k time samples, and there are m subsymbols. So these k time samples are actually located onto k subcarriers. So these k subcarriers are actually given with only a green color with one, because it is a subset. Because if you look at this one, k equal to n into m, k into m, and k number of subcarriers, some number of frequency samples. So only one block consists of m frequency samples. Okay, there are k number of subsamples, and in this m frequency samples, the horizontally there are k time samples. So k time samples multiplied by m frequency samples will give you your total n. Both systems are carrying only n time samples. But how we are dividing? We are dividing in x-axis as well as in the y-axis. That is the difference in frequency division multiplexing. So pictorially we can see how it looks. What is the difference from OFDM to GFDM? So in OFDM, my data samples at the 0th instant. One time I started my transmitter. So at the 0th instant, I am observing 4 data samples. So for these 4 data samples, I have added a cyclic prefix, right? Because if you remember your diagram, at the end of your I50 block, there is an addition of a cyclic prefix. There is an addition of a cyclic prefix. Then at the next time interval, again 4 data samples, a cyclic prefix. Like that, as the data stream comes in, I take serial to parallel construction and I map accordingly. After mapping them, I port onto the endpoint FFT. Here in my case, maybe 4, n equal to capital N equal to 4 point FFT. So on to the top, after that 4 point FFT, I add additionally a cyclic prefix. Okay. Now GFDM. So what the GFDM is taking? At 0th time instant, I take 4 instances of my data. That is D0 to D1. At first instant, I take D0 to D3. At the second instant, I take D0 to D3. At third instant, like that, I take time slots. I divide it into time slots. On each time slot, the same data samples, but these time slots, they are generating different data symbols because at different time instances, the data symbols are also going to change, right? So all these data symbols are added with only one cyclic prefix. All these data symbols are added with only one cyclic prefix. Whereas in OFDM, after FFT block, we add a cyclic prefix. So as the data comes in, I add cyclic prefix. As the data comes in, I add cyclic prefix. Here for my entire time slots and for my subcarriers, I add only one time cyclic prefix. That means there is a huge saving of your bandwidth. Unnecessarily, we are allocating some amount of bandwidth to your cyclic prefix. That is one of the advantages in GFDM. So how it is executed, this GFDM? Just go through the block diagram. So this block diagram, maybe this is the total view of the block diagram. Okay, so I can show you the block by block. So if you look at this block diagram, there are actually the difference from GFDM to OFDM. You wait till n number of data samples, right? So these n number of data samples are ported onto your IFFT block. That means there involves only one capital N. But whereas in this case, I have to wait till n into m subsamples, because on each subcarrier, we are transmitting these data symbols using different modulo filters. Okay. So what is that modulo filter? Just look at this modulo filter. So I have raised D0, all D0 samples of m subsymbols, 0 to m minus 1 subsymbols are given, placed at different intervals, delta of n, delta of capital M minus 1 to n. They are located at different intervals. So these values, each sample is modulo operated by your filter, that is Gn of mod cap of nm, Gn of mod cap of nm. Then these m subsymbols are modulated onto a single carrier. That's the beauty of it. That is exp of 0. That means one carrier. The subcarrier is 0. So these 0 subcarrier data is given to your GFDM modulator. Summed up. Like I'll take next stream of Epsom symbols. We'll map the stream of Epsom symbols into a prototype filter and we'll port it onto the next subcarrier. So that means your understanding is on each subcarrier, there is a capital M number of subsymbols, right? Total, how many subsymbols you are transmitting? N into M, that is capital N into capital M number of subsymbols you are transmitting. At the end, we add a cyclic prefix. At the end, we add a cyclic prefix for your GFDM. That is the difference from GFDM to OFDM modulator. So we use different filter banks. And we use different filters, pulse shaping filters. So if you look at the pulse shaping filter time frequency response, for this one is for RRC filter. For different values of alphas in my RRC filter. Okay, sir. So we would see the power spectral density, how as alpha is increasing, the out of band leakage is also going to reduce. So this is the entire mathematical modeling of your GFDM model. So we take all these operations into consideration, like upsampling, the pulse shaping, and subcarrier upconversion into a single matrix notation, that is X equal to A into D. And how we design that X is known as a transmitter modulated matrix. And this in this transmitter modulated matrix is actually a NM cross M filter matrix containing the G's, as I said in the beginning. These are the G's, right? This is the G of N mod NM. Those G's of length NM and successive columns are shifted versions. And we take a diagonal matrix, is NM cross NM diagonal matrix. Use diagonal elements are actually concatenated copies of the vector, that is e power j's. 1 e power j 2 pi by n and so on and so forth. And D is the vector of size. I said NM into 1 data blocks we are transmitting over 1 GFDM symbol. This is a stack of elements of all the vectors. So we concatenate all these values. It moves to X equal to A into D. This is the format. And I receive this signal. That means R equal to HX plus W. H is my channel. X is the data, what I transmitted. W is the noise. So this H is actually the padded version of H, because we made N into M length. So your channel length also, if it is N into M, your decoding scheme will become very easy. So to be organized in such a way, it becomes N into M, and I receive the signal, that is FFT of R, FFT of H, then I compute the IFFT. So we can estimate your Ds using a normal receiver, a MMSC receiver, and zero forcing receiver. So these are the 3 different equations for my GFDM modulator. So, and also we derived a probability of error equation for the GFDM symbol error rate. We obtained this formula for probability of error. And also we have seen the noise enhancement factor for GFDM. And we compared the performance of a multi-tapper GFDM, which improving the orthogonality in GFDM. Okay. And also we have considered a multi-tapper GFDM. That means the filter bank is changed and with a new filter bank. Then we have seen the different structures of the outputs of the probability of error also computed. And we have seen what are the parameters we set for GFDM and GFDM DPSS. Also for GFDM and OFDM, the parameters are same. For GFDM GPSS, the parameters are slightly changed. That is, the DPSS filter bank is used, and we have obtained different results for GFDM. So if you look at this GFDM tapper, simulations and the original values are matching 1-to-1. Okay. So this is about a GFDM. So if you have any doubts, please ask me some questions on GFDM because it's already 4. So 1 more hour is left out. I can take to the new communication scheme.
Sure, ma'am. Ma'am, there is a question in chat box. Even in FBMC also, we use filter bank in 5C.
Okay.
Then GFDM is better or FBMC is better?
This is an entirely different structure, right? GFDM and FBMC are different structures. So I would say GFDM comparison with FBMC, GFDM gives much, because here the cyclic prefix is only at one time. So we are saving the bandwidth, and also it gives a better performance than the other one. The only thing is the complexity is increased, because we have to modulate those data into the prototype filter. Then after prototyping, we'll port that data onto the same carrier for M subsymbols. So similarly, if there are suppose n number of carriers, on each carrier 5 subsymbols are ported at a time. That is the main difference from GFDM to FBMC. Where FBMC is same as OFDM. Only thing is, at the end, to localize your frequency spectrum, we use a filter bank. But whereas in this case, it is entirely a different structure. Okay, so I cannot compare with the FBMC and GFDM, because the complexity wise GFDM is more complex. The FBMC is not that complex. Only the main difference from FBMC to the OFDM is we use a filter bank at the end.
Okay, ma'am.
So any other questions?
No more questions, ma'am. Participants, if anybody is having any queries, you may interact directly with them by unmute yourself.
Okay, just
Hello, ma'am.
Yeah. Tell me.
This is Sarana Kumar calling from Madanapalli Institute of Technology.
Yeah.
May I know what is the next level of LTE, madam?
We are currently in LTE advanced, right?
Yes, we are in the currently LTE, but not in the 4G. May I know what is the next level for LTE?
So the next level for LTE is 5G.
Madam, actually, my friend is actually this question I asked yesterday morning also, madam. My friend is working in Samsung Noida. He's working under the protocol of 6G. May I know what is the type of application is it better to use for 6G?
So for 6G, it is beyond 5G, right?
Yeah, so now they are working, madam. Actually, the protocol is ready. My friend is making the white papers also.
Okay.
But he is not revealing because of the confidentiality of the company.
Yes.
Yeah, so may I know what is the advantages of 6G?
Even more, much faster. The latency is 1 millisecond. Less than 1 millisecond you are expecting in 5G. So in 6G, maybe 0 millisecond.
Ma'am, how this will be helpful for the IoT and artisan regions people's this communication?
Everything is again through research. So you generate papers, you simulate.
Any current research papers are available related to this, madam?
Which one? GFDMC?
It's about the 6G network.
Yes, yes, you can see many papers in IEEE.
Okay, thank you, ma'am.
Yeah. So just a minute, I'm just charging my laptop. Okay. Okay. So now I start with another. So he is one participant is very curious about 6G, what 6G looks like, right? So maybe I can throw some light on 6G, how it works. So we are looking for new applications because there is a millimeter wave band is available, right? And even the lot of the spectrum is already overcrowded. So what next? How can I use my other applications into communication? So okay. This is one of the new area, the visible light communication. So as one person is asking me about what about 6C, what kind of applications you are going to use. So
Madam, yes, ma'am. I heard about this one also, madam. Li-Fi.
yeah.
We have Wi-Fi, we have I-Fi and Li-Fi.
Yes.
Yes, L-I-F-I. Yes, ma'am. I heard about this one, ma'am.
Yeah.
Yeah, ma'am.
So I'll tell you in a simple way what is this visible light communication. Because everywhere when you are going, we need lot of bandwidth, right? The bandwidth is almost crowded. There is no space to give you personally to use for your applications because of many narrowband IoT devices are want to connect to the internet at the same instant of time. It is not possible. Then what is the other alternative? So other alternative is you have to search for new technology. You have to search for somehow I want to communicate my signal and I have to search for the frequency band. So there is a huge bandwidth is available in light. So this huge bandwidth available in the light, I can throw you some spectral analysis, spectral frequency components of my light wave. So if you look at this light here, as we are increasing the frequency is like 10 to the power 0 to that is long radio waves, then AM waves, so FM waves, right? Already these radio waves up to 10 to the power of 8, 10 to the power of 6 to 10 to the power of 8, the radio waves are already filled. Then we are into 10 to the power of 10, that is microwave. So in nanometers, it is 10 to the power of minus T. So this microwave is already filled because we are using for satellites, other microwave applications. Then infrared. So infrared is covered with your remote TV remotes. We are already using infrared band is also filled. Then what is the next band? The next band is visible light spectrum, right? This is the blue color, blue, red and green is a visible light spectrum. So this blue, green, red visible light spectrum, we have not used this one for communication. But rest of all already we have used for the communication. Infrared we are already using it. Microwave we are using it. FM/AM we are using it. Long radio waves also we are using it. Then the next band is ultraviolet. Already we are using it for some health applications, X-rays, gamma rays, like that, right? So many rays are available. So everywhere the application exists. For in the ultraviolet rays, so in this band, there is in the visible spectrum, there is no application available. So this visible spectrum is actually working at 400 nanometers to 780 nanometers, 780 nanometers wavelength band. So that means in terahertz band. Okay. So this band we can use it for your communication purpose. That's what people thought of. And even in 5G, this is one of the application where a new application, because entirely a new communication, we want to start it. So this new communication is possible through your normal light emitting diodes and a photo diode. So what the light emitting diode does and what the photodiode does. So just I'll give a brief writing of your light emitting diode and a photodiode. Okay. So I have just I'm saying that I want to communicate because my communication is always in alternating currents, right? We do modulation, we do take digits, we do modulation, but ultimately when we are sending to the through the antenna to transmit over the air, it must be a sinusoidal waveform. So I am taking the end sinusoidal waveform. So maybe my end sinusoidal waveform looks like one waveform. This is my waveform I want to transmit. So I am saying that devices. What are the devices? Light emitting diode. LED, we know very well what is LED, light emitting diode. And I know that a diode takes photodiode. So if light falls on it, it emits. When this emits light, this takes light. Okay. So here, for emitting light and taking light, I want to use this LED and photodiode, PD, photodiodes. So when light emits from here and it falls here, so these changes, if I can observe through some circuitry over here, if I can send my information through this diode, my transmission is done. That means it is a wireless channel. This whole is wireless channel. Okay, at least for a long, at least for short distance communication in a building, suppose. So it is already overcrowded. Wi-Fi is already overcrowded. There is no space for the Wi-Fi. Any new mobile is entering into the hotel room, it cannot access the Wi-Fi because of the huge number of devices already connected to the Wi-Fi. Okay, then how to combat these problems in how do you manage your communication link? How do you do that communication? These are all important for us. So, okay, so then we know the fundamentals. What is the fundamental? LED can take only positive current. It cannot take a negative current. That means it allows the positive direction, but it won't allow the negative direction. It won't allow the negative direction. Right? But my communication is in sinusoidal format. My waveforms are in sinusoidal format. So how do you manage that one? At least not a sine. I am sending a rectangular pulse. So it will allow only positive, but it cannot allow negative. Then, so what is the other alternative? So somehow when I am passing the signal through LED, it is connected, a sine wave is connected through the LED through some biasing, right? It allows this current and this light falls on the LED. So that is photodiode. The photodiode will give you the output in the form of your half-wave rectified waveform. This is half-wave rectified waveform. This one is missing, right? Then you do lot of variations to your sign such that somehow my voice would reach to the photodiode. So one form of doing that one is you have a sine wave. I have a sine wave. So if you 0 is here, if you shift this 0 to down, then means the total thing is becoming positive. Then if the total signal is positive, the diode can allow this positive signal. Okay. So that means clipping, clamping. So I used a clamping to my signals so that it can forward through my diode. It falls on the photodiode. I can receive my signals. These are all so I can do some communication, right? So this way I can do my communication.
Ma'am, thank you, ma'am. I get your point, madam. Madam, I like to do research on this area. May I know which softwares, emulators or simulators are helpful for me to do the preliminary work?
So I'll share my screen because I'm already somehow. So what the work we have done at our laboratory, I'll share it with you.
Ma'am, in the meanwhile, I'm requesting the organizer, please give the recorded videos for us, madam, because this is very excellent session. So please give the recorded videos for us, madam.
I think they are already recording.
Yeah, recording is going on, madam, but I'm requesting the organizer to forward this one, madam.
Sure, sir, sure.
Forward it.
Thank you, madam. Thank you so much.
Okay. So this is the way, right? So this spectrum is available, and because my time is also going ahead, quickly I'll go through this comes under optical wireless communication, okay, because I'm using optical devices. So the name is also optical wireless communication. So this Li-Fi modulation, if you are I can go with normal, all your communication streams can be directly adapted to your optical also. So when you are adapting to the optical, you have to bring some changes to your signals. That's it. If you can bring some changes to the signal, I can transmit my signal. But the length of your communication link is short. I cannot communicate more than a kilometer. Maybe I cannot communicate more than 1 kilometer as well, because it is only light, right? So when you are transmitting the light, the ambient light, that is your sunlight, also the present that sunlight also falls on your photodiode, then how to take care. There are many issues are possible, many issues, challenging tasks are there in this optical wireless communication. So if you look at this diagram, if you look at this diagram, you can see that the life-wave modulation scheme, I can go for OFDM, I can go for other multi-carrier communications, I can go for color domain modulations also in visible light communication, like ACO OFDM, PAM DMT, UFDMT, OFDM, UFDM, ACO OFDM. There are many thousands of variants are already people are finding out. They are giving their research problems. They are publishing their papers. We too publish some papers in this. So we did some little work on this optical OFDM. So what we did in this optical OFDM is we take a source data, QAM modulator, and we did some subcarrier alignment. Then why do we need this subcarrier alignment? I will tell you. So what is the additional block? IFFT is there, QAM there, source is there, cyclic prefix is there. Only additional blocks are in this for optical OFDM is subcarrier alignment and unipolar conversion. So these are the new additions to this one. Similarly, in the receiver, we use subcarrier as extraction because assignment is done, extraction is done. Then unipolar is not required because it's already falls on the optical device. I take care for my unipolar output. So I'll call it as DCO OFDM. Okay, so this DCO OFDM, direct current optical. DCO means direct current optical OFDM. I'm using some technique because it is a multi-carrier communication. That is IFFT. IFFT I'm using it, right? So in this IFFT, suppose you give a signal to the IFFT block. I give a 1 and 0 or 2 ones, maybe 4 ones to 4 point IFFT. What is the output of my IFFT? 1, 1, 1, 1 I am giving as input to my IFFT block. What do you expect at the output of your IFFT? Some answers from some feedback from you, from the participants through chat box. Kiranmayi?
Yes, madam.
Is it connected to YouTube live?
Yes, ma'am. Yes, ma'am.
Yes, madam.
No, it's not correct.
No, ma'am. Okay.
Because